Okay, so welcome, and now we're going to introduce the theorem, the comparison test. And so I'm going to go through both points, and then we'll do a proof of point number one. Okay, so here's a comparison test theorem. One, suppose there exists an integer capital N such that this is always true for all n greater than or equal to n. Okay, so again, so some symbolism. This means there exists. This upside down A is the symbol that we use for all, right? So it says suppose there exists an integer n such that this relationship holds, this inequality holds for all of the nth terms for all n greater than or equal to capital N. Then, in that case, if the series with b sub n converges, which is bigger, right? All the terms are bigger, then that would mean that the other series of a sub n also converges, okay? Theorem 2 says suppose there exists an integer n such that this relationship is always true, that the nth term of this a sub n is bigger than or equal to the nth term of b sub n for all n greater than or equal to n. Then if the series of b sub n diverges, well, since it's smaller, right? It's always smaller than that. If that series diverges, then that would cause the other series of a sub n to also diverge. Because look at it this way. If I have a graph, right, and I have partial, let's say partial sums, right, and I'm plotting the partial sums. Well, you can see that if I have the partial sums for, let's say, let me do different colors here. So if I have, let's say, something like this, right, so here are the partial sums for, let's say, for b sub n, right? These are the partial sums for b sub n. And the green dots are the partial sums for a sub n. Well, if we know that this one converges by using one of the other tests, let's say it's a p-series or it's a geometric series or something like that, and we know that that one converges, well then it causes the other one has to converge if it's always less than, right? So that's important here. Okay, so if this is always less than this partial sum, and this partial sum is converging to a number, then this would also have to converge. Now, to what number we don't know, but the point of this theorem is that, hey, if this is true, then if the bigger partial sum is converging, that means it's got a bound. That means the other series is bounded, which means it must be also converging. Now, similarly, if we have case 2, and we have something like this, right, which would be indicated by something like, maybe something like this, right? Oops, wrong way. Oh yeah, that's fine. This will work. And if we have something like this, where we have a sub n is always bigger than b sub n, like for example in this case here, right? So if a sub n is always bigger than b sub n for all n bigger than n, then if the smaller partial sum diverges, then that's going to force the other term, the other series that's larger, to also diverge. And so if the smaller one is unbounded, that causes the larger one to also become unbounded. Okay, so that's a little visual to help explain and understand where this theorem comes from. Okay, so now in the next video I'm going to prove the first case. Now to prove the second case, it's just the contrapositive of the first case. Okay? So I'm just going to do the first one, and then you could do the second one by contrapositivity. Okay, that's it. Have a great day. I will see you next time.